All right, 2005 Subaru Impreza WRX. And what we're doing is a switch input circuit design review. And in section 2 in my book, I mentioned that there are 2 different ways to identify switch inputs. One would be a wiring diagram, and we follow the wire that doesn't go to the computer. We'll always tell you what design it is, whether pull up or pull down. And the second one is using a voltmeter. So I want to show the voltmeter part. This one's a little bit more complicated than I hoped for, because the back unit of this switch assembly, it has all the power windows and the door lock and one main plug, so it's not just like a 2-pin connector that you can look at, but it's still the same concept. And what we've done already is we've identified the 2 wires, the lock and the unlock wires, and that's the yellow and the blue with a green tracer. That's these 2. And so if I put my voltmeter on the yellow wire, you see we got 11.35 volts, and I put my voltmeter on the blue with a green, and I have 11.35 volts. And as I hit the lock button, you can watch it. That's the lock. So 11.35 when I'm not hitting the button, and basically 0.03 or 0 volts when I do. Move this to, and that's the auto range. I hate the auto range. Move this to the yellow wire, and this should be the unlock side. And holding it in the unlock position, you see our basically 0 volts, and let go of it and it's 11.35. Now, we don't know circuit design yet. We don't know if it's pull up or pull down. This next test is going to be what's going to tell us that, and that's going to be with the switch unplugged. And so I'm just going to unplug the connector, and we'll get a voltage reading on these 2 wires with this unplugged. I need a third hand. Okay, is that still in the shot?
Yes.
All right, so you see with the connector unplugged, so this would be with the switch unplugged. On the yellow wire, we're reading 11.35, and on the blue with the green tracer, we're reading 11.35. So what we know about this circuit design for these door locks is it's a pull down design. Knowing it's a pull down design is critical for diagnosis. Let's say the door locks didn't work at all. You could have opens in the signal wires, you could have bad switch, you could have bad ground, and half the battle is to know that the circuit design's pull down, and that when you unplug the switch, it should be 11, 12 volts on that signal wire. And that tells you the computer's good, the wiring integrity is good all the way out to here. And then the rest of your checks would involve checking the switch ground, and then checking the switch itself. All right, so what I want to show, since we know circuit design now, can you hand me that test light up there? I want to show how to use a test light and do a bypass test, which is basically what I call being the switch. So in this case, my test light's going to get connected to a ground, and what I'm going to do is I'm going to pull these circuits down through my test light, and the computer should react as if the switch was there, and it should lock and unlock the doors. When this test is valuable would be that you're pretty confident. Let's say you're about 90% confident you need a switch, and you just want to make sure that the computer's okay and the wiring's okay. And this is going to make you that much more confident to put a switch in this thing if this test reacts like it should. And so is this still in the camera? Are we good?
Yeah.
So my test light's connected to ground. I'm leaving the voltmeter on there so you can see that I'm actually going to pull it down through my test light. And I touch that wire and the door locked. And I'll put the test light on it again. You see I'm pulling that all the way down through my test light. Is my test light in the shot too?
Yes.
All right, one of the things too that you notice is that's a 12 volt feed. But it's not enough to light the test light, because remember, on pull down circuit designs, there's that current limiting resistor inside the computer, and that causes a huge voltage drop in the circuit. And so this is basically like just taking a jumper wire to ground. Could I use a jumper wire and do the same thing and hit that wire and do the same test? And the answer is yes, you can, and it would be safe. But the reason I don't use a jumper wire is in case you touch the wrong wire with your jumper wire and it's a hot wire, you know, you're gonna blow a fuse. Or, you know, worse yet, if you run the wrong polarity with a jumper wire to a computer and it's not an input, it ends up being an output, you can fry the driver and the computer, and that would not be a good thing. So that was the lock. And then the unlock one, we'll put the voltmeter over there so you can watch them both. Take the test light, and there you go. Pull down design, switch input, bypass test. To do a bypass test, you need to know circuit design. I need to know the polarity to put my test light to. If it was a pull up design, I'd put my test light to battery positive. If it's a pull down design, I keep my test light on ground. And really what this does is it makes you so accurate in what you're doing. If these door locks didn't work before and you can do this test, you have two choices left. You either have a bad switch or you have a bad switch ground. Now, how would we address the switch ground? Because I guess I might as well show that since we're here. The switch ground in this case is a main ground in this whole unit. In this whole unit, there's a heavy gauge black wire right here that is my switch ground. But it's not just the switch ground for the door locks, it's also for the rest of the switches on this panel. And you see we're reading 0.01 of a volt on that ground. That's not a good test. And the reason that's not a good test is the circuit's not loaded. Now I'm doing ground to ground voltage drop tests. Voltmeter lead's connected to ground. The other voltmeter lead is connected to the switch ground. It's not a good test until I activate the switch. So when I turn the switch on and I either lock and unlock the doors, see how my voltage stays very low? Now I'm seeing a slight voltage increase, but a slight voltage increase would be normal because there's now current flow on that ground. But did you notice how low the voltage stayed? That would be how you check your switch ground. Switch ground is good. If in this case, the door locks didn't function at this point, you checked your switch ground, you did your bypass test on the two wires, you're done. Put a switch in it. 100% confident. Pull down, switch input, circuit identification, using a voltmeter, and showing a bypass test. Okay, I want to add one more comment to this system, that this is a computer controlled door lock system. The test that I just showed you would not apply to a conventional door lock system that was not computer controlled. What we're dealing with in this case is a switch input that the computer does all the work. This door lock switch in no way, shape, or form carries any of the current flow for the door locks like a lot of the cars are. This is simply a switch input to a computer, and the computer's going to react and control the door locks accordingly. So again, this test that I showed, this is for a computer controlled door lock circuit. It's for any switch input that is a computerized switch input. This is how you deal with a pull down design. All right, so this is this 2005 Subaru that we just shot the pull down circuit design switch input. And I wanted to show the diagram to go with it because there's two different ways to identify circuit design, and that's using a wiring diagram or using a voltmeter. And so here's the diagram part of it. And what we want to do first is find the switch. Looking for my, not the door switch, but I'm looking for, here we go, driver's side door lock switch is where we were working. One of the things to point out too about Mitchell wiring diagrams is the dotted line on this. So you see it says driver's side door lock switch, and then there's a dotted line. The dotted line shows you a partial view, and I think that's pretty evident now that we showed you the car part of it, that there was a lot more than 3 wires going to it. And you can see it's pin 5, pin 8, pin 9. In any case, dotted line is a partial view of that component. So looking at the driver's side switch, we have a switch and it's a dual position switch. This thing's either going to move this way or it's going to move this way. And so that is the common feed wire, is the black wire. So we can highlight that first. And this black wire, you can see it's a shared wire with another component too, but let's follow where this black wire goes, and it'll kind of give you an idea of what we found on the car, which is, it is a ground. Okay, so everything attached to this ground, this black wire, by the way, this dotted line right here, a little bit more on a Mitchell diagram, this dotted line tells you there are other grounds that share that splice, similar to partial views of components. But what we know is this common wire is a ground, okay? And what we said about using a wiring diagram for circuit identification, why can I not clear that? There we go. Is the signal wires, the wires that go to the computer, or in this case, here we'll just do one of them because that's going to be a little bit too cluttered. I'll just show the lock or the unlock. I'm not sure which one that is just yet. The yellow-red wire, I'll show you that one where it goes. It's shared with the passenger door, which would make sense. Both of those either switching to ground, which is what this is doing, because our black wire is a ground. Either one of those two is going to do the same thing to this splice, to this circuit. Let's follow this up top, and it goes to this left side of the dash. It's an integrated module, they're calling it. And it also comes over here to a keyless entry module. So it actually goes to two different modules. But the point though with this one is you can't know circuit design by looking at the signal wire. We don't know what the circuit design is. We know what the switch is doing to it. Now that we see that it's grounded on the other side, this switch is pulling it to ground. This is a pull down design. That's exactly what we found on the car. Okay, one other thing to add, I guess, in here is one of the things about switch inputs that I'm trying to emphasize is that switch inputs don't control anything, that the computer just watches what the switch does. And if you look at the circuit design a little bit more zoomed out, you can see all of the door lock motors and the actuators for the doors. And go in a little bit more. So you got your left front, your right rear, left rear, and then rear gate. So they're all electric motors. And if you look at them all, you know, a lot of it's shared, of course, because we're unlocking them all at once. But if you look at the controls with them, all of those motor controls come back to this integrated module. So this is the guy that's going to be doing all the work with these electric motors. What's carrying the current flow for the electric motors, the door lock motors on this car? This integrated module is doing it. So there's no relays involved. There's transistors, reverse polarity circuits inside this module that's going to control the door lock. So how does that work as far as the signals go? This yellow wire is the one we had highlighted on our driver's door lock. If you follow this yellow wire at this splice, it comes into this integrated module right here on this yellow-red, right? Did I do that right? Yellow turns to yellow-red, okay. Pin 11. So when this module right here, there'd be a voltage sensing circuit, and it would be like this. There would be a resistor, and there's a source. And our source in this case, we'll call it 12 volts. I know we were reading 1135, but just for theory purpose, we'll call it 12 volts. And inside of this module is a type of voltage sensing circuit, which I'll just draw as a voltmeter. And the way the circuit's designed is when this module sees 12 volts on this voltmeter, it knows that you're not wanting the door to be unlocked or locked. It's in a natural state. As soon as it sees 0 volts, what's its reaction? The module's reaction is going to come down here. I forget which three. Was it these 3 wires? And it's going to activate the door lock motors in the correct polarity based on that input. And so you can see that the switch itself isn't carrying any of the current flow to these door lock motors on this design. That's why we call it a switch input, is it's an input to a computer. It's not controlling the current directly. So it's all done in here. The module does it. There's going to be transistors in here that do that based on this input, the yellow, red, and what was the other one? The other input was this, well, it was change color on us, didn't it? Light green changes to red and white. I guess that's something else to point out here too. There's a connector right here that changes color on this, and that can be misleading, because if you're doing ohm testing, let's say open and short circuit testing, and you're looking at a light green wire on this side, and when you follow it up on the other side, it turns to red and white. So if you were doing, an ohm test between pin 9 and pin 12, the colors changed on you. Those are things to pay attention to. So that's it. Electronic or computer controlled door lock circuit. Okay, I've had this video done for months now, and I haven't posted it because I felt it was missing something. And what I wanted to just briefly explain to you guys is what this second module was doing over here. So we're talking about this keyless entry module. So what I've done is I've copied and pasted some of the diagram, put it on one page, put in a little bit of drawings here, and I'm not using my smartboard, so I'm doing this with my little mouse pad on my laptop, so I really can't draw very well. But what I did is I drew a transistor inside of here, and I'm pretty sure that this is the way this works, so just bear with me for 1 second. We discussed pull up, pull down circuitry, and you can see that my integrated module looking over here is the one that does all the controlling. I mentioned that in the previous clip, that the reverse DC electric motor, all the door lock motors are reverse DC electric motors, and they're controlled by this integrated module. And also that I believe the sensing circuit is part of this module, and I described it as a 12-volt pull-down design. And so if you look at this diagram, there's really 3 places that this door lock circuit gets a ground. One would be the driver switch. We described that, this being a ground wire right here, and that switch is going to move this way or it's going to move this way. It's going to ground the circuit, and I'm just showing the yellow-red wire just to keep it from being cluttered. And that would be either my lock or unlock circuit. So the driver's door would be one. The second one would be the passenger door, and I kind of cut that off here, not a big deal. You get the idea, it's the same as the driver's side. So either location, if it grounds it here or if it grounds it here, same thing's going to happen up here at this module, is on the other side of that resistor, it's going to drop to 0 volts, and the computer's going to react and exercise the door locks. Now the third one, I believe, is this integrated, or sorry, the keyless entry module over here, that picture this blue arrow that I just drew here as your transmitter button. You hit the button, you send a radio frequency signal into this keyless entry module, and it's going to react, and it's going to, I believe, have a transistor that's going to also ground this same yellow-red wire. And so that would be your third location of a ground, either there, there, or there. And if we get a ground in any one of those 3 locations, the same thing is going to happen up in here, that this module is going to see it, it's going to react, and it's going to do its job. So I didn't think I did a good job explaining that, what this guy was doing in that video. And the reason behind that, when I saw this, I was hoping for a more simple design, because I'm trying to reinforce a topic here, pull up, pull down circuitry,
And when you throw another control module in here, it kind of muddies it a little bit. But hopefully that gives you at least a little bit better idea what's going on here. But as far as the main points of this go, it doesn't change. For circuit identification using a wiring diagram, looking at the wire that goes to the computer never tells you what it is, because they don't draw the stuff I drew here. This stuff does not exist on these diagrams. All you have is a wire going to a computer. What is it? What's its design? You don't know by looking at the signal wire. You follow the wire that does not go to the computer, and in our case, if you remember, this splice ended up going to a ground. So it is a pull down design for sure. And it really doesn't matter if it was this module or it's this module, but circuit design is still able to be done by following those principles that I'm teaching in section 2 in my book, Switch Input. So hopefully that cleared it up a little bit. I think with this additional information, I'm going to be happy with the whole thing, and hopefully you guys like it.